In the last class, we discussed two topics. We discussed electrical currents and we discussed electrical resistance. Those two topics are going to be the building blocks, the basis for today's class. In today's class, I want to talk about some basic electrical circuits that involve batteries and involve resistors. Specifically, I'm going to walk through these four bullets here. We're going to talk about batteries and the idea concept of the electromotive force. We're going to talk about resistors when they're in an arrangement we call a series arrangement in a circuit, and resistors when they're in an arrangement that we call a parallel arrangement in a circuit. And then finally, we'll move on to this fourth bullet in which we look at more complicated circuits, which have both parallel and series components made out of resistors and batteries. So that's going to be the plan, and we'll walk through these items on the plan. If you want to imagine the type of circuit that we want to solve, as an example, imagine the electrical circuits in your home. So the electrical circuits in your home distribute electrical current, distribute electrical potentials, distribute electrical power, energy to various components in your home, to the lights, to the heaters in your home, to the stove in your home, to the washing machine and the clothes dryer, wherever they are in your home, and to the TV and computer and so on. We're going to solve the problem of exactly how much current, exactly how much potential, exactly how much power and energy gets distributed to the components in an electrical circuit. We're going to analyze electrical circuits and analyze the details of the currents, voltages, power in the electrical circuits. So the first topic is batteries, and part of that first topic is electromotive force. So we give the symbol epsilon. So what is a battery? What does it do? What is the electromotive force? What does it do? From the point of view of energy, the action in the universe, what's going on in the universe, is changes, transforms of energy. So from the perspective of energy, what's going on in the universe is energy being transformed or changed from one form to another, or changed from one owner to another. There's no energy being created or destroyed. It's just being moved from one form to another form, from one owner to another form. A battery, electrical battery, is a particular device that transforms chemical energy to electrical energy. Whereby chemical energy, I mean the energy that's associated with the bonding of the individual electrons in an atom or molecule. And where I mean by electrical energy, I mean the energy that's associated with the flow or the movement of electrons or charge carriers through a material. So that's the energy perspective, and that's what batteries do in the energy perspective. One way of thinking about batteries is to imagine this picture sketch over here on the right-hand side. This sketch is showing a gravitational battery, but we could think of an equivalent electrical battery. So a gravitational battery would raise mass, what experiences the gravitational force, to a higher gravitational potential and a higher gravitational energy. Likewise, a electrical battery, it raises not mass but charge, what experiences the electrical force, to a higher electrical potential, a higher electrical energy. And so the gravitational battery here, the water well, and an electrical battery for 1.5 volts, a 9 volts battery from Kroger's, they do similar things in raising either mass or charge to higher electrical or gravitational energy. In the case of the battery, we can write down the following equation for the workings of the battery in terms of what we call the electromotive force. And downstairs, I've written here an equivalent equation for the working of the gravitational battery in terms of what I called a gravimotive force. Now, electromotive forces just means that electricity is providing some energy for the motion of electrons around the circuit, falling downhill as they roll around the circuit. The gravimotive force, what I'm calling it, is just my word for the gravitational force, providing some energy to some mass so that it can, say, roll down a gravitational potential hill. The electromotive force is defined as the amount of, or the change of the electrical energy that we gave the charge when we raised it up, divided by the amount of charge. And actually, that's a quantity we've already met. That's the change in electrical potential. And so that change in electrical potential, as a charge crosses between the terminals of the battery and is raised from lower to higher electrical energy in the battery, that's what we call the electromotive force. Likewise, as an analogy, we might define a similar gravimotive force. It would be the change in gravitational potential energy when we raise a mass up to some higher elevation, divided by the mass of that mass. That would be the change in gravitational potential, and that provides some possibility of the mass rolling downhill. There's some sort of gravimotive force. Now, there's all sorts of batteries, all different brands of batteries. There's, for example, alkali batteries that you know from Kroger's. There's lithium batteries that are in laptops and in phones and in iPads. I'm not going to talk about the details of a alkali battery or a lithium battery. The details are a bit complicated, but I want to give you an idea of how we can turn chemical energy, chemical processes into electrical energy and electrical power in a battery by showing you a couple of examples of rather simple batteries. This first battery that I pictured both over here on the left and over here on the right. This first battery I just made by putting together two different metals. And I chose zinc and nickel because they're common in batteries. So if you take a look at the left-hand picture, which is like the before picture, I've just put together the zinc and the nickel in close contact, in contact with one another. That's the initial condition. Now, the zinc is full of electrons that can move around, and I've indicated those with the little green dots here. The nickel is also full of electrons that can move around. I've also indicated those with the little green dots here. Now, in the zinc, there are equal number of electrons as there were protons in the ions of the zinc. And in the nickel, there are equal number of electrons as the protons in the ions of the nickel. And so electrically, our zinc was initially neutral, and our nickel was initially neutral, both with equal numbers of electrons and protons. That's the initial condition I've indicated downstairs here. Now, we've already met when talking about glass rods and cat's fur and plastic rods and silk that some materials have high affinities for electrons. They like to acquire electrons, say when rubbed. Other materials have a lesser affinity for electrons. They may like to give up electrons when rubbed. That was an explanation of how rubbing a glass rod with cat's fur or a plastic rod with silk, how that charges up the glass or the plastic or the silk or the fur. The same applies for metals. Zinc has some sort of affinity for electrons. Nickel has some sort of affinity for electrons, and it's a fact, it's an observation that zinc has a higher affinity for electrons, zinc has a lesser affinity for electrons. So if you put the zinc and the nickel in contact, some electrons will move from the zinc side to the nickel side. Now, when they move from the zinc side if they're electrons leaving the zinc, they're going to make the zinc positively charged. If they're going to the nickel side, those arriving electrons will make the nickel negatively charged. So the end result is that the zinc will become positive, less affinity for electrons. The nickel will become negative, a greater affinity for electrons. Now, it doesn't go on forever. All the zinc electrons don't walk over to the nickel side. It doesn't go on forever because as zinc electrons move into the nickel region, a potential difference due to the charges of the zinc and the nickel, the corresponding potential difference between the zinc and the nickel builds up. And that is like a hill that the electrons would have to climb up. And you end up with an equilibrium between the zinc electrons wanting to diffuse over to the nickel side because of the greater affinity of nickel, the lesser affinity of zinc, and the zinc electrons not wanting to climb up the hill that they would have to climb up to get from the zinc side to the nickel side. And that's the equilibrium. The end result is some potential, maybe 1.1 volts, between the zinc and the nickel sides. And we built a battery. We built a battery that is the source of a potential difference. We built a battery that is the source of an electromotive force that could drive a current around a circuit. Here's the second battery. This is an interesting battery. It's not made of two different metals. It's made of pure water and salt water, out of which I constructed a battery. I put them in some sort of container with a semi-permeable membrane separating on the left the salt water from on the right the pure water. Now, when I pictured the pure water, I just pictured it as pure blue, pure water. There's no impurities in the pure water. There's no ions in the pure water. But when I pictured the salt water, I pictured it as a combination of sodium ions and chlorine ions, the salt. So in red, I've indicated the chlorine ions, which are all negative. And in green, I've indicated the sodium ions, which are all positive. And I've also indicated that the chlorine ions are relatively large. The sodium ions are relatively small. And that size is important because the sodium ions can get through the semi-permeable membrane between the pure water and the salt water. But the chlorine ions are too big to get through the semi-permeable membrane between the pure and salt water. So the initial condition looks like this, with ions on the left-hand side, the equal number of sodium ions and chlorine ions from the dissolved salt, and no ions on the right-hand side in the pure water. But what happens? What happens is that the ions are diffusing around, the chlorine ions on the left, the sodium ions on the left, they're diffusing around. The sodium ions can pass through into the right-hand side of the pure water. And so they diffuse through to the right-hand side, but the chlorine ions can't. They're too big to get through the semi-permeable membrane. The end result is that we build up a positive charge over here on the right-hand side. We start accumulating sodium ions, and we build up a negative charge on the left-hand side because we got an excess of negative chlorine ions. Now, again, this doesn't go on forever. We don't have all the sodium ions walking over to the right-hand side. As sodium ions move from the left to the right, well, there's a charge build-up on the left and right, negative and positive on the left and right. That means that there's an electrical potential that grows on the left and right. That electrical potential becomes a hill that the sodium ions have to walk up. And so we end up again with an equilibrium between the sodium ions wanting to diffuse through the semi-permeable membrane, but that diffusion involving climbing up a hill, which the sodium ions don't want to do. They don't want to climb up that potential hill. And so we get some sort of equilibrium of a positive charge and negative charge on the left and right. we get a equilibrium potential difference between the left and right. We build a battery again. This is the type of battery in a cell. So in a cell in the human body, there is fluid inside the cell, fluid outside the cell. These fluids have different concentrations of ions. There are holes or pores in the cell. The cell is wall, membrane is semi-permeable, and by some ions being able to get through the pores or the holes and other ions not being able to get through the pores and the holes, we build up a charge difference on the inside and outside of the cell. We build up the electrical potential and then between the inside and outside of the cell. So this is a natural battery. Now let's move on to talk about resistors. I'm going to talk about resistors in an arrangement we call a series arrangement. I'm going to talk about resistors in an arrangement we call a parallel arrangement. We'll do resistors in the series arrangement first, and then we'll do the resistors in the parallel arrangement second. A natural example of resistors in series are the sections or segments of either the axon or the dendrites of a neuron. So axons, dendrites, they come in little segments, and those little segments act as resistors, and they are resistors in series. The axons and the dendrites of these resistors in series. So that's a natural example of what we're going to discuss. So I've got 3 slides on series resistors, and then I've got an example. And then we'll have a few slides on parallel resistors and also an example. So this first slide on series resistors is just to introduce the idea of what resistors in series actually is. And secondly, what is the equivalent resistor for a arrangement of series resistors. So those 2 topics. Then we'll worry about, the understanding of the current and the voltages across and through the resistors, and what is the equivalent resistance in terms of the individual resistors. Over here on the right-hand side, this is what we call a series arrangement of resistors. We've got R1, R2, and they are in series with one another and this battery here to form this complete circuit. If you were an electron going around this circuit, you'd start out at the negative terminal and you'd head round through this resistor on the right, this resistor on the left, and back to the positive terminal on the on this side of the battery here. So you went through both resistors, and that's what we mean by a series arrangement. That means all the current is going through both resistors, and that's a feature of a series arrangement. The equivalent resistance for this circuit, and that's depicted over here in this circuit diagram, where there's just this single equivalent resistance replacing these 2 individual resistances. There's still the battery. The equivalent resistance is the one that for the same applied voltage, you've got the same battery on the left and right, draws the same electrical current. So the same current over here on the right as there is on the left. The keys to do with understanding series resistors, whether it's a pair of series resistors or multiple series resistors, 3 or 4 or more series resistors, has to do with current, has to do with voltage. The key thing regarding current is that the same current goes through the resistors, the series resistors. So the same current I is passing through resistor R1 as is passing through resistor R2. No current is lost or gained between R1 and R2. And so that's a key feature of a series circuit of resistors. On the other hand, second point down here, the voltage from the terminals of the battery, the voltage difference from the terminals of the battery, that's applied between A over on the far left and C over on the far right, that's shared between the 2 resistors. So resistor number 1 gets some fraction of it. Resistor number 2 gets the remaining fraction of it. If they were equal resistors, it would be actually equal fractions. But if they're unequal resistors, then they don't get equal fractions, but they do get a total voltage that adds up to the applied voltage from the battery here. So the equivalent resistor in this arrangement is getting the same current as we described as going through R1 and R2. So it also gets the current I. It gets the total voltage that is being applied across the series resistor network. So the sum of the voltages across R1 and R2 is equal to the total voltage across the equivalent resistor. Based on that understanding, and I won't derive it, I won't show you how to derive it, but based on that understanding about the currents through the two resistors being equal, the voltage across the two resistors is being shared by the two resistors, some on one, some on the other, you can figure out, you can derive the equivalent resistance in terms of the individual resistance is that the equivalent resistance is just the sum of the individual resistors. So if we've got two resistors, the equivalent resistance is R1 plus R2. It's as simple as that. If you have multiple resistors, supposing you have 3 or 4 or 5 or more, then the equivalent resistance is just the sum of all your series resistances. So if it's 3 resistors, R1, R2, R3, it'd be R1 plus R2 plus R3. So that's the equivalent resistor when you've got resistors in series. A couple of facts about it is that equivalent resistor is always bigger than the individual resistors. So you've created a larger resistance by putting two resistors in series. It makes sense as a larger resistance to the current flow because now instead of the current just having to flow through R1 and the resistance of it, or just flow through R2 and the resistance of it, it now also has to flow through the sum of them, R1 and R2. So that will be more resistance. So it would be like water flowing through a hose. You've got two hoses. If it flows through one of the hoses, just that one, is a certain resistance. If there's flowing through a second garden hose, that's another resistance. If you chain them together, put them in series, there'll be more resistance to the water flowing through the two hoses connected together. Let's look at a quick example of series resistors, a circuit involving series resistors. Here we are. We've got a 6-volt battery downstairs here on the bottom left. We've got two resistors in series upstairs here. On the left-hand side, R1 is 2 ohms. On the right-hand side, R2 is 4 ohms. Question asks us some basic facts about the circuit. We're going to calculate the currents through each of the resistors. We're going to calculate the potentials across each of the resistors, and we're calculate the electrical power dissipated by each of the resistors. I'm going to do that by first calculating actually something else that's going to be useful. I'm going to calculate that equivalent resistance. That's going to be very useful. It's the first step in figuring currents, potentials, and powers in the different resistors. So on this little diagram here, I've drawn on the left-hand side the original circuit again, 2 ohms, 4 ohms, R1, R2 in series with the battery. On the right-hand side, I've drawn the equivalent resistance, that single resistor that draws the same current for the same applied voltage. I've labeled my R1 and R2 as 2 and 4 ohms. My battery is 6 volts. The equivalent resistance, what's that? Is straightforward. It's just the sum of the two individual resistances. It's R1 plus R2, so that's 2 plus 4, that's 6 ohms. That's the equivalent resistance. That's my very first step. Now I can worry about the questions that were asked. What's the current through R1 and R2? What's the voltage across R1 and R2? What's the power dissipated in R1 and R2? And we're just going to walk through those. We're going to walk through those in that order because it's actually easiest to solve them in that order. And so that's the route that we're going to go. When we talk about parallel resistors, it'd actually be easier to solve the same 3 questions in a slightly different order. So we'll see that. Anyway, we're going to start with the currents. We're going to start with the currents because the currents are the same. That's the reason we start with the currents. The current through resistor number 1 is I1. It's the same as the current through resistor number 2. That's I2. And we said it was the same as the current through the equivalent resistor that we just call I. The current through the equivalent resistor is easy to figure out because we know the voltage across that resistor is 6 volts. Because we know the resistance of that resistor is 6 ohms, we just got to take Ohm's law for that equivalent resistor, divide the voltage across that resistor, 6 volts, by the resistance of that resistor, that's 6 ohms. That gives us 6 over 6, 1 amp is the current. That's not only the current through the equivalent resistor, but as we said, as we explained, it's the current through the resistor R1, the resistor R2, and the equivalent resistor. What about the voltages? The voltages are easy and straightforward to figure out for R1, R2 now, because we know the currents through R1 and R2, and we know that they obey Ohm's law. That's the relationship between current and voltage. So if you know the value of a resistor is resistance, and you know its current, you can find its voltage. Or if you knew its voltage, you can find its current. So let's use Ohm's law. V equals IR. We're going to apply it to the first resistor. So all these subscripts are ones for the first resistor, the voltage across it, the current through it, its resistance. The current through it is that 1 amp. The resistance of it is the 2 ohms. 1 times 2, that's 2 volts across that first resistor R1. Do the same thing for the second resistor. That second resistor, applying Ohm's law, the voltage across it, V2, is the current through it, I2, times its resistance, R2. The current through it is 1 amp again, same current as through R1. The voltage across it is the resistance of it is 4 ohms. It's upstairs here. So 1 times 4 is 4. 4 volts is the potential. You notice we got 2 volts across the first resistor, 4 volts across the second resistor. The sum of 2 and 4 is 6, which is the 6 volts supplied by the battery. It must be that way, that the full voltage of the battery is shared between these two resistors in some unequal way because they're unequal resistances. Now we can calculate the power that's dissipated by the first resistor and the second resistor. Remember, they are dissipating energy, they're dissipating power. They're getting warm as the electrical currents flowing through them. They're turning electrical energy of the flowing current into thermal energy of the jiggling around electrons in the resistors. So what's the power dissipated in resistor number 1? I'll call that P1. The equation for that in an electrical circuit is the product of the voltage across it times the current through it. We know the voltage across is 2 volts. We know the current through it is 1 amp. So that's 2 watts. Watts is joules per second, the energy per second. We can do the same thing for the power in the second resistor. Again, that power I'm going to call P for power, subscript 2 for the second resistor. It's the voltage across the second resistor times the current through the second resistor. We know the voltage is 4 volts. We know the current is 1 amp. 4 times 1 is 4. It's 4 watts, 4 joules per second. This picture shows an analogy to the current flowing through series resistors, the analogy with water flowing down this waterfall. So in series resistors, the current, the electrical current, is flowing through each resistor. Here, the water current is flowing through each step. Here, in a series circuit, the electrical potential is shared between the individual resistors. Here, the difference in height is shared between the individual steps of the waterfall. So there's a direct analogy between the distribution of electrical potential and the distribution of electrical current for series resistors as there is between the distribution of the elevation of the height and the distribution of the water current through these series steps in a waterfall. Now let me move on to resistors in parallel. Classic example of resistors in parallel is the ion channels in a cell membrane. So a cell membrane is this big bag that separates the conducting intracellular fluid from the conducting extracellular fluid. That bag has lots of pores in it. Those pores or holes, ion channels, act like resistors. Those resistors are all in parallel with one another. And we'll see what parallel means, but that's an example, a classic example of parallel arrangement of resistors. Again, I've got 3 slides. The first slide is just want to introduce what parallel is for resistors, and also what the equivalent resistance is in the case of a parallel circuit. And then we're going to talk about the keys to the parallel circuit. Again, there are keys in terms of voltage and current. And then we're going to lay out the equation for the equivalent resistor in terms of the individual resistors in a parallel circuit, and look at an example. So over here on the right-hand side is a parallel circuit of 2 resistors, R1 and R2, connected in parallel to the terminals of this battery. By parallel, we mean that, say, the right-hand terminals of the 2 resistors are directly connected by wires to the negative terminal of the battery. The left-hand terminals of the 2 resistors directly connected to the positive terminal of the battery. If you're an electron that is leaving the negative terminal of the battery, you either go through resistor R2, you take this path here, or you go through resistor R1, you take this path here. So any particular electron either has to go through R1 or R2. That means that the electrical current flowing around the circuit, some of the electrons will go through R1, and some of the electrons, or the remainder, will go through R2. And so that we can see the current being shared in a parallel arrangement. That's a key idea. The equivalent resistance to this parallel circuit is the single resistor. I could replace this pair of resistors with R1 and R2, that for the same applied voltage, for the same battery downstairs here, would draw the same current. This current here would be the same as the total current out of the battery over here on the left-hand side. That's what we mean by equivalent resistance. The keys to a parallel arrangement of resistors are again about current and voltage. Let's start this time with voltage. It's the easiest one to see. The voltage across the resistor R1, the voltage across the resistor R2, and the voltage across the equivalent resistor are actually all the same. So resistor R1, its left-hand terminal and right-hand terminal are just directly connected by wires to the battery. Same for resistor R2. Its left-hand terminal and its right-hand terminal just connected by leads to the terminals of the battery. And the equivalent resistor likewise. Its left-hand and right-hand terminals are just connected by leads, by wires to across the terminals of the battery. So all those 3 resistors, R1, R2, and the equivalent resistor, have the same potential across them, and it's the battery potential. On the other hand, that total current I that's passing through the equivalent resistor can only go through the equivalent resistor. That's the only way to loop around the circuit. In the parallel circuit arrangement, some of that current I, we call it I1, goes through the upper resistor. The remainder of that current goes through the lower resistor. So in this parallel arrangement, I1 plus I2, these 2 individual branches of current, arms of current, they are equal to the total current from the battery, the total current through the equivalent resistor. That leads to an equation for the equivalent resistance in terms of the individual resistors. Again, I'm not proving this, I'm not deriving this, but it's based on those rules for how the voltage is distributed, how the current is shared between the resistors. The equivalent resistor for a pair of resistors, well, it's reciprocal, 1 over the equivalent resistor, is simply equal to the sum of the reciprocals, the sum of 1 over R1 plus 1 over R2. So that's the simple rule for the equivalent resistor of 2 resistors. If you've got multiple resistors, supposing you've got 3, or you've got 4, or you've got 5 or more, then the equivalent resistor, its inverse, is equal to the sum of the reciprocals or the inverses of the individual resistors. So that's this equation here. So it applies generally not just to 2 resistors, but to 3, 4, or more. Important comment about the equivalent resistor is that it's smaller. It's always smaller than any of the individual resistors. So here, the equivalent resistor would be smaller than either R1 and R2. That's the reverse of the series arrangement, where the equivalent resistor was bigger than R1 and R2. A quick example for our equivalent resistors, for our parallel arrangement. In this circuit here, I've given the resistor R1 2 ohms. We met that before. Resistor R2 4 ohms. We met that before. And again, I'm applying a 6 volt across them. But this time, they're connected in parallel across the 6 volts rather than connected in series across the 6 volts. We're going to work out the same 3 things. We're going to work out the currents through the resistors, the potentials across the resistors, and the powers dissipated in the resistors. We're going to do it in a similar way. We're going to first work out something that's really going to help us. We're going to think about that equivalent circuit of the 2 resistors with the equivalent resistance, and we're going to figure out its value, the value of the equivalent resistance. That way, that will allow us to solve these individual questions about the individual resistors, the currents, the voltages, and the powers through them, dissipated in them, and across them. So here's my redrawing of the original circuit with the 2 and 4 ohms across the 6 volt battery. They're in parallel. Here's the equivalent resistance, and here I am computing. 1 over the equivalent resistance is 1 over R1 plus 1 over R2. Well, 1 over R1 is 1 over 2, which is a half. 1 over R2 is 1 over a quarter, 1 over 4. 1 half plus 1 quarter. What's that? 1 half plus 1 quarter is 3 quarters, but that's 1 over the equivalent resistance. So I want 1 over 3 quarters, which is 4 over 3, or 1.33. That's actually the equivalent resistance. Notice it's smaller. It's smaller than the 2 ohms, and it's smaller than the 4 ohms. We always make a smaller equivalent resistance with parallel arrangements. And the equivalent circuit then is a 4 over 3 ohm, or 1.33 ohm resistor in series here with this, or connected across the terminals of this 6 volt battery. Now we know that, we can go on and solve the questions that were asked. I'm going to start with voltage this time. Last time we started with current. We started with current last time because the current through the resistors was the same. We're going to start with voltage this time because the voltage across the resistors is the same. So we start here. The voltage across resistor number 1 is the battery voltage. It's the same as the voltage across number 2, which is also the battery voltage, which is the same as the voltage across the equivalent resistor, which is again the battery voltage. They're all 6 volts. That's just, we can see that in the pictures. No equation formula we need there. We just see it in the pictures that the resistors are connected across the terminals of the battery. If you know the voltage across a resistor and you know its resistance, you can, using Ohm's law, find the current. We did this for the previous series arrangement, but there we knew the current through the resistors and we found the voltage. Now we're knowing the voltage across the resistors, we're going to find the current. The current through resistor number 1 by Ohm's law is the voltage across it divided by its resistance. So that's 6 volts divided by 2 ohms. So that's 3 amps. That's the current through I1. The current through I2, that's the voltage across it, divided by the resistance of it, 6 volts over 4 ohms, that's 1.5. 1.5 amps. So those are the 2 currents. At this point, we know the voltages across the resistors. We know the currents through the resistors. If we want the power dissipated by resistor number 1, all we've got to do is multiply the voltage and the current through that resistor and across that resistor. That's V1 I1. So it's 6 volts times 3 amps, 18 watts. That's the power dissipated in this top resistor R1. Power dissipated in resistor number 2, again, just got to multiply the voltage across it by the current through it. That's V2 I2. V2 is that same 6 volts multiplied by 1.5 amps. That's 9 watts. So we're dissipating 9 watts from from electrical energy to heat energy in the second resistor R2. And so we've solved the problem. If you want an analogy, a water analogy to electrical current through parallel resistors, think of the water current in this river. In this river, it's entering here on the bottom right, and then it streams upstairs here to the top right. But in the middle of the aerial photograph, you see the river takes two paths around the island. There's this one on the upper left, and there's this one on the lower right. These two paths are like two parallel paths through two parallel resistors in a circuit. These two paths have the water current rather than electrical current shared between them. Some of the current is going upstairs here, and some of the current is going downstairs. However, they have the same decrease in elevation from the where they enter, the currents enter these two paths to where they leave these two paths. The water elevation, the water height, is the same when it comes out of the upper estuary compared to this lower estuary here, this upper path compared to this lower path here. Finally, here's a quick quiz question that is a quiz question based on the circuits we've actually just been describing. We've got two circuits, one on the left and one on the right. The circuit on the left has a battery, 1.5 volts. The circuit on the right has a battery, 1.5 volts. The circuit on the left battery is connected across two resistors that are 2 lamps here, and the same is true of this battery on the right. Its circuit involves these 2 lamps here, but in the one on the left, they're arranged in parallel, and in the one on the right, they're arranged in series with one another. And the question is, does the circuit on the left dissipate more power? Does the circuit on the right dissipate more power? Or do the two circuits dissipate the same amount of power? And so we want to figure that out. There's multiple ways you can figure this out. And I don't know what the best way is. The best way is whatever works for you in figuring this out. But one way I thought about it is that to think about the voltages that are applied in the circuit on the left and the circuit on the right. The voltage is applied across both. The voltage of the battery is applied across this resistor here upstairs and this resistor here. So they both get 1.5 volts across each of them. So there's 1.5 volts across this top resistor and 1.5 volts across this bottom resistor. Downstairs here, the 2 resistors, the 2 lamps, have to share the voltage. So the 1.5 volts, only 3/4 of a volt is applied across this resistor, and the remaining 3/4 are applied across this resistor. So the resistors in the left-hand circuit have twice the voltage across them. And the resistors in the right-hand circuit have half as much voltage across them. Well, if the resistors have twice the voltage on the left-hand side, they'll also have, by Ohm's law, twice the current that's flowing through them. And they'll actually have 4 times the power dissipated in them because the voltage is twice as big and the current is twice as big, and power is current times voltage. So we expect to get 4 times as much power here. For the resistors on the right-hand side, they only have half the voltage. If they only have half the voltage, then they're only going to get half the current flowing through them. And therefore, they only get 1/4 of the power. Again, the power is current times voltage. The current was half as much on the left-hand side, right-hand side. The voltage was half as much on the right-hand side. So the power is actually 1/4 as much. So 4 times more power over here on the left, 4 times less power over here on the right. You can see it. Look, these lights on the left are lit. These ones on the right-hand side are barely lit. Maybe you can see a dim glow of these. I want to move on to a more complex circuit. And I want to solve this more complex circuit just by thinking of a particular example of the complex circuit and going ahead and solving it. because we're going to just use the rules that we developed for the simple series parallel circuits. So let's take a look at this circuit here. This circuit here looks like a difficult circuit to solve. It looks like a complicated circuit. It's got one battery, that's okay. But it's got 5 resistors in this circuit. And if you look at this arrangement of 5 resistors, it's a spaghetti of resistors. It's resistors in series and resistors in parallel, combinations. How are we going to solve that? To solve this, we're going to solve it by first finding the equivalent resistance, which is what we did in the last 2 problems with the simple series circuit and the simple parallel circuit. So we're going to find the equivalent resistance. And then once we find the equivalent resistance, we'll be able to figure out currents, voltages, powers in any components of the circuit. For example, we'll figure out the current that's supplied by the battery here. That'll be one thing that we'll figure out. We'll figure out the voltage across this resistor R1 here, this 10 ohm resistor, and we'll figure out the current through this resistor R5 over here. So those are just examples of a current and a voltage through different resistors. But we could figure out anything. We could figure out anything once we know the equivalent resistance for this particular circuit. I said it's scary, but once you know the approach to it, it's not so scary after all. This one slide here, it's me with my therapist. We're trying to figure out how to solve complicated problems. She's giving me some problem advice. The point is that generally circuit problems, are not simple series circuits, not simple parallel circuits. General circuit problems are combinations of both. They involve both series, parallel combinations. To solve a complicated problem, to solve a complicated circuit problem, second bullet here, we want to identify parts of the circuit, little parts of the circuit, small sections of the circuit, that are, say, simply series circuits, or say simply parallel circuits, and replace them with equivalent resistors. And we want to do that over and over again. Just keep looking at the circuit, seeing if there's some problem, part of the circuit you can solve. Some pair of resistors in series, you can replace them with a parallel arrangement, series arrangement, single resistor arrangement. Or two resistors in parallel, can you replace that with a single equivalent resistor? And if you keep doing that, keep solving the little problems, you find that overall, you'll solve the whole problem. You'll end up with one single equivalent resistor in series with a battery, connected across the terminals of the battery. You'll have solved for that equivalent resistor. You can find out the currents drawn from the battery, given the voltage of the battery, and then you can go ahead and apply Ohm's law, your knowledge of Ohm's law, to any of the other resistors or components of the circuit and find the currents through them, the potentials across them, the power dissipated in them. So that's the basic approach here. Our first problem is to solve the equivalent resistance of the entire network. And as I say, we're going to do this by step simplifying that complicated circuit of 5 resistors to smaller and smaller circuits, meaning circuits with smaller numbers of resistors, by using our rules for resistors in series and rules for resistors in parallel. And I've done that here. It took me 3 steps to get to the equivalent circuit from the original circuit. But each of those 3 steps was relatively straightforward. I've labeled the intermediate steps from the initial circuit A as B and C, to my final path to the equivalent circuit with a single equivalent resistor. That's circuit D here. So let's see how I did it. I've kind of ringed resistors that I've combined. In the first step, I'm combining 2 resistors in series. The next step, 3 resistors in parallel. The final step here, 2 resistors in series to get this equivalent resistor. Look, I looked at the original circuit with the 5 resistors, and I spotted I've got R4 and R5 in series with one another. If you're an electron, you have to go through R4 and R5. So these are in series. The current going through R4 and R5 must be the same current. So these are in series, and I can combine them to make a single equivalent resistor. For series resistors, the equivalent resistor is just the sum of the resistors. So I've got 5 ohms plus 20 amps is 25 ohms. And so in the second sketch, I'd replace the two resistors R4, R5 with a single resistor R45, the subscript meaning it's a combination of R4 and R5. That's 25 ohms. Once I did that, I spotted now I've got 3 resistors in parallel with one another. This portion of the circuit in this green ellipse has R2, R3, R4, 5, all connected in parallel. All of the top terminals of those 3 resistors are connected together by wires. All of their bottom terminals are connected together by wires. So they are indeed in parallel. The same voltages across each of them. That's what parallel means. And I can combine them by the rules of combining parallel resistors. The equivalent resistance, I'm going to call it R2, 3, 4, 5, because it really is equivalent to those 4 resistors. The inverse of that equivalent resistance is the sum of the inverses of these 3 individual resistances. So it's the sum of 1/10 for 1/10 ohms, 1/5 for 1/5 ohms, 1/25 for 1/25 ohms. I won't go through the details of the common denominator here, but it's 17/50 inverse ohms is the sum of these 3 fractions. We need the inverse of that because we just calculated the inverse of the equivalent resistance. The inverse of that is 2.9. We can replace these 3 parallel resistors with one 2.94 ohm resistors. It draws the same current for the same applied voltage. That's equivalent circuit C. Now we're almost there. We've just got 2 resistors left, the R1 on the left, the R2, 3, 4, 5 on the right-hand side. We note now these 2 are just in series with one another. An electron leaving the negative terminal goes through R1 and must go also through R2, 3, 4, 5. And so this is a series arrangement. And so the rules for combining series resistors can be applied to this. We've just got to add together the resistance R1, the resistance R2, 3, 4, 5. That's 10 ohms plus 2.94 ohms. So the total resistance, the equivalent resistance of the entire network of these 5 resistors that look so awful is just 12.94 ohms. And we just did it by breaking the problem up into lots of little simple steps of series and parallel resistors and solved a big complex problem that way. Now we've got the equivalent resistance. We can answer some of the other questions that were posed in the problem. The first question that was posed in the problem was current drawn from the resistor. And then the second and third questions were about individual resistors, R1 and R5, the currents and the voltages across them. So let's start with the current drawn from the battery and actually the power that's supplied by the battery. Here's the equivalent circuit that I'm going to think of. It's the 25-volt battery across the terminals of the 12.9 ohm resistor. If we want the current that's flowing around this circuit, well, we can just focus on this resistor here and apply Ohm's law. The voltage across that resistor is known, 25 volts. The resistance of that resistor is known, 12.9 ohms. If I apply Ohm's law, V equals IR to this resistor, the current equals V over R, where V is the voltage of the battery, R is the equivalent resistance. I can fill in the 25 volts, fill in the 12.94 ohms, and I get a current that's a little bit less than 2 amps. It's 1.93 amps. If I wanted the power the battery is supplying to the circuit, all I need to do is multiply the voltage across the battery times the current through the battery. We now know both of those. We were told the battery voltage is 24 volts, 5 volts. We figured out the current is 1.93 amps. Multiplying those two together, here we are, gives 48.2 watts. That's the power, electrical power, that's being supplied to the circuit. Came from chemical power, is going to be dissipated into heat, thermal. Finally, I want to solve the two remaining parts of the problem. The first question in the remaining parts was, what is the voltage across the individual resistor R1 in the original circuit? The second part in the remaining part of the problem is, what is the current through the resistor R5 in the original circuit? I'm going to do this in both cases by comparing two different circuits that involve equivalent circuits and using that to help me solve the problem. Let's see how it goes for finding the voltage across R1. The two circuits I'm going to compare are the final equivalent circuit with just one equivalent resistor. It's this circuit upstairs, and it has the battery connected across the terminals of the single equivalent resistor that was 12.9 ohms. And we had figured out that 1.93 amps was flowing around this circuit through the battery and the resistor. It's a current that's supplied by the battery and dissipates power in the resistor. Then the second circuit I want to compare this with is this circuit down here. It's one of the equivalent circuits on the way to this final circuit. Actually, it's the one just before this final equivalent circuit. It contains these two resistors that are in series with one another, connected across the 25-volt battery. So it's the resistor R1 we're interested in, and then this resistor R2345, we called it. It was the combination, the equivalent to the four other resistors in the circuit. The purpose of comparing these two arrangements is that this is a single resistor circuit and a pair of resistors in series circuit, which is the very problem that we started with when we started looking at resistors in series with one another. And we said there that the current through the equivalent circuit, which is 1.93 amps in this case, is equal to the current in this original circuit. And i.e., it's equal to the current that flows through this resistor R2345 and this resistor R1. And so we know without any calculations that the current through R1 is the same as this current through this equivalent circuit here. That current, I call it I1 here, is equal to I, this current upstairs here, 1.93 amps. Now, at that point, we know the current through the resistor R1 that we're interested in. We know the resistance of the resistor R1 that we're interested in. The only thing we don't know is the voltage across the resistor R1. We can solve that just with Ohm's law. So just a quick application of Ohm's law, that V1, voltage across R1, equals I1, the current through R1, times the resistance of R1. So that's 1.93 amps times 10 ohms, which is 19.3 volts. That is the voltage across this resistor here. And so that's how we solved this part of the problem. We used a couple of circuits, an equivalent circuit and another equivalent circuit, and we used those two circuits and ideas of resistors in series together with Ohm's law. Let's go on to the next part. The last part of this problem involved determining the current through one of the 5 resistors. It was resistor R5. To figure out the current through R5, I've drawn 2 circuits here. The lower circuit is actually the complete circuit that we started with, involving the 5 resistors, so including R5. The upper circuit is the first step we did in making equivalent circuits, and it's the circuit where we combined the series resistors R4 and R5 into a single resistor upstairs here. We called it R45. So those are the 2 circuits I've drawn. And I've drawn those 2 circuits because the important point about that first step of combining resistors 4 and 5 in series to make resistor R45. The important thing for this part of the problem is that the current through R5 is the same as the current through R4, because they're in series, and is the same as the current through R45, because it's their equivalent resistance. And so the problem of finding the current through R5 can actually be reframed as finding the current through R45. And we're going to work with that circuit rather than the circuit containing the separate resistors R4 and R5. So our new task is to find the current through this resistor R45 with 25 ohms. If you look at the upper circuit in the right way, you can see that we can straightforwardly find the current through R45 if we know the voltage across R45. That will give us, by Ohm's law, the current through R45, and we can find that voltage by looking at the circuit. So take a look through the outside arm of the circuit. I'm tracing it out here. Let's start over here. If we walk through the outside arm of the circuit, we go through the battery. So there's a 25-volt change in potential as we walk across the terminals of the battery. We walk across the top arm of the circuit, but there's no components. It's just a wire. We walk down the right-hand side of the circuit, and there's a voltage change due to the resistor R45. We walk along the bottom of the circuit, there's nothing. There's no components along the bottom of the circuit. And then we walk back up towards the battery, we're going to pass through R1, the resistor R1, and there'll be a voltage change across that. As you walk around the voltage, as you walk around the outer loop of the circuit, you realize that outer loop is just a loop containing a battery and two series resistors. One of them's R45, where we want to know the voltage across it. The other one's R1, where we already know the voltage across it. And so the basic idea for finding the voltage across R45 is that 25 volts from the battery is being shared by R1, the resistor R1, and the resistor R45, because they're in series with one another. And since we know that resistor R1 has 19.3 volts of it, then the remainder must be the voltage across R45. And 25 volts minus 19.3 volts, I've written it down here, is 5.7 volts. So the voltage across R45 is 5.7 volts. Well, then, if you know the voltage across a resistor, and you know the resistance of the resistor, it's easy with Ohm's law to find the current through the resistor. The current, according to Ohm's law, is the voltage divided by the resistance. So it's the voltage across R45 divided by the resistance of R45 will give us the current through R45. And so it's 5.7 volts divided by 25 ohms. That's 0.23 amps. So that's the current that's flowing through this resistor R45. But we already argued that it's also the current flowing through the two resistors that were in series that R45 was equivalent to. And so the current through R5 and also R4 is going to be equal to that 0.23 amps. And so we solved that part of the problem. These last two parts of the problem were both actually solved by thinking of equivalent circuits and applying Ohm's law to those equivalent circuits. Once you've got the equivalent resistance, all the rest of the problem was really thinking about equivalent circuits from the one with all 5 resistors to the one with just 1 resistors and the circuits in between, and applying Ohm's law to those circuits.